Up until this point, I've been showing you EKGs graphed on a traditional coordinate axis system. That's this guy. X and Y axes, each with their own definition and scale. In the context of an EKG, we always understand that the horizontal axis will be time and the vertical axis will be voltage. And since we've got that assumption, and for economy, we can just work on graph paper. Standard EKG paper has millimeter boxes, or sometimes dots, with heavier lines at 5 mm increments. In the old-timey days, when a mechanical stylus ran over an unrolling bit of paper, you calibrated your time axis by changing the speed that the paper unrolled. We still hold that standard today. EKG paper is 25 millimeters a second along the horizontal axis, or 1 second is 5 large boxes, that's 25 small boxes. Each small box, which is again 1 millimeter, is 0.04 seconds or 40 milliseconds. If someone is going to test you on this, I'm afraid you're going to have to remember it. But if you can remember 25 millimeters a second, you should be able to derive everything else if you're quick on your feet. This speed can be changed, and you'll sometimes see it done in EP labs. Speeding up the time axis makes it look like energy is moving more slowly, and sometimes that will allow you to see more detail because the tracing is spread out. There's some rare utility to slowing the paper down, though why anyone would configure that to be the only option is beyond me, but it is a quick and effective tool for treating bradycardia. You're safe to assume that your paper is running at 25 millimeters a second unless it's strongly indicated somewhere else. And circumstances where that would occur are vanishingly rare in EMS, unless your partner's a jerk. We'll quickly look at how to measure time difference using the paper here. The quickest way to get an approximate electrical rate is by using the 300 rule. Find a prominent EKG part that lines up with a line. Here we'll use the R wave, I'll define that in a little bit, and we measure to the same part on the next beat. If two beats are one large box apart, the rate is 300, 2 would be 150, 3 would be 100. So for this example, we're somewhere between 100 and 150, closer to 100. If we wanted to be too precise, we could divide 1500 by the number of small boxes. There are 1500 small boxes in a minute. There are 14 small boxes here, so 107.1429. Those 9 ten-thousandths of a beat per minute are very important. If it were 7, this patient would be dead. Let's say you have an irregular rhythm like this mess here. If we count the R to R intervals, we'll find that they're all different. Is the heart rate 136, 250, or 83? The answer is both all of them at once and none of them, right? Instantaneously, it could be any of them, but in general, when we're trying to judge if something is too fast or too slow or just right, we're more concerned about a longer period of time. A good approach here is to run a 6-second strip, count the beats and multiply by 10, or use an even longer strip if you have lots of runs and gaps. And please always verify the presence of a physical pulse as well. Most EKG paper has tick marks at either the 1 or 3-second marks drawn on the outside border for your convenience. It's also worth noting that most, if not all, cardiac monitors derive their displayed heart rate from the R to R interval. So, depending on which one it catches and how long it averages, you may end up with totally off-base numbers displayed on your screen. This is particularly common with irregularly irregular rhythms. One of my starting goals for this project is to get you all to a point where you can look at an EKG and sense what's wrong on a quick glance, and then follow up and figure out what's wrong in detail. This takes a lot of time and a lot of not-so-quick glances, but rate is a great starting point for being able to eyeball quickly, and then go back and take the measurement when you suspect something is wrong, or if you're just not sure. Before we talk about anything else, let's talk about nothing. The point which we're measuring changes in amplitude or voltage on an EKG from is the electrical baseline. The baseline is defined by the point where there is no cardiac activity occurring, or, more specifically, where there is no current along a given lead. In an alive person, that time is normally the time between two cardiac cycles. What we'll learn in a bit could be called the TP segment. Movement of the baseline that is not associated with cardiac activity can be thought of as noise on the EKG signal, information that is interfering with the information that you want. This is an example of what's called wandering baseline. The baseline itself is moving, so everything else is moving along with it. This isn't a cardiac problem, it's a data problem. In this particular instance, the frequency of the movement of the baseline is likely the patient's respiratory rate. As the patient's chest expands and contracts, the electrodes move back and forth relative to each other, and this means that the resistance of the chest wall changes, or impedance if we want to be more specific. That's the other variable in Ohm's law that we've ignored so far. Modern EKG machines can normally correct for this, but the same phenomenon is used by some devices to measure respiratory rate. This is the centered brown electrode that you see on some hospital telemetry systems. In this circumstance in particular, the monitor will eventually catch up and actively cancel this wander out. So we'll get to how that actually works someday, maybe. I guess at some point I'm going to have to tell you what the right leg electrode does, don't I? We needed to define all of this before we talked about the vertical axis on our paper, because the vertical axis measures voltage, and voltage changes on the EKG are usually relative to the baseline. Each millimeter is 0.1 millivolts, so 2 large boxes, that is 10 small boxes, is 1 millivolt. In common parlance, voltages are almost always expressed in millimeters rather than in millivolts. So unlike time, where we talk about milliseconds and seconds, instead of saying 0.2 millivolts of ST elevation, we're normally going to say 2 millimeters of ST elevation. That one, at least, I think is a little easier. And finally, I'm going to recommend one product here, which is the RCAT EKG Badge. This I like in particular because it's a well-designed measurement tool as opposed to just a reference card. The times in the real world where you actually need to measure something are few and far between, but this is great for after-call discussions and starting to build out intuition. There's a link in the description. It's about $10 as of this writing. Obviously not sponsored, and it's not even an affiliate link.